Hello. So last Thursday, we began a problem where I was going through the problem solving process in terms of how to approach different problems where you've got forces in multiple dimensions. Now, we got about halfway through this problem on Thursday, but for a complete and self-contained video, I decided that I would start from the beginning here and go through the entire thing again. I would encourage you to review this problem before Monday's class so that you're refreshed and familiar, because next week we're going to go through and practice some of these. So there's a lot going on here. It's very easy to get overwhelmed. And so the first thing to remember is from our problem solving process is don't panic, right? We don't want to panic. There is definitely a lot going on here, and we need to deal with it all, maybe, or maybe there are parts we don't need to deal with. And it's very easy to get overwhelmed. How do you avoid that? Well, a couple of good first steps are, one of our other things is processes is begin with a principle, right? Now, what principle do we maybe want to begin with in this situation? Well, we can look at kind of what we've got going on. We have quite a few forces in the problem, and ultimately, we want to know how far is the spring stretched at this moment. So, given that we also know that the force of a spring from the spring on an object, in this case a block, is how far I stretch it times its stiffness. This is from Unit 1, or just the first few weeks. It seems logical that we want to begin with a principle that has to do with forces. So let's start with our good old Newton's second law, that forces are what cause objects' motion to change. And now we, continuing with our problem solving principles, we want to do one thing at a time. That's going to be a very common theme throughout this video. So let's pick something to do. I'm going to deal with my vector symbols first. Now, the vector symbols, what do those imply? They mean directions matter. The way you deal with it is deal with them separately. With X and Y separately. Now I'm going to use our usual coordinate system where X is to the right and Y is up. So let's follow that along. So we have the sum of the forces in X. All right, I want the other pen, I think. The sum of the forces in X will be the change in the object's motion in X, and the sum of the forces in Y will be the object's change in its Y motion. So AY, how much its motion in Y changes. Pushes in the vertical direction, only change the vertical. Pushes in the horizontal, only change the horizontal. Next, I have to choose something else to deal with. One thing at a time is very much the sort of overriding philosophy here. One thing at a time. There's, even now, we still got a lot. We've got a sum, we've got an F, we've got subscripts, lots going on. So let's choose something to do and just focus on that. I'm going to choose to deal with the sum here. So what does the sum tell us to do? The sum tells us, switch that. I'm going to deal with the sum, like I said, but I want the colors to be consistent. What does this say? It says, look at all forces in X and add them up. That's what this is telling me to do. Sum all the forces in X and add them up. For that, a free body diagram might be quite helpful. So let's go and do that. We had some practice with this last week. So my diagram, I have a force of weight from the earth on the block down. I have, of course, my tension from this rope on this block. There's some normal force from the floor pushing on the block, keeping it from falling through. We have a spring on the block pulling to the left. The block is stretching the spring as it goes. And we also have a force of friction from the floor on the block to the left, right? As it slides across the floor, there's going to be a frictional force that opposes the motion. The whole thing is moving this way. Now, looking at our free body diagram, what forces act in the X direction? Our friction is in X. Our spring is in X. And our tension has a component, a part of it, in X. And a part of it is in Y. So there's a force of tension from the rope on the block in the Y, and there's a force of tension from the rope on the block in the X. So this X part is relevant for what we're doing now. So putting all those in, we have the force of friction pointing to the left. So I'm going to give it a negative sign. It's pointing in the negative X direction. That's from the floor on the box. Don't forget all your subscripts and everything. They're going to be helpful. We have a force of spring from the spring on the box to the left. And then to the right, we have a force of tension from the rope on the box, but we're only interested in the horizontal part, the X part. Now, I could go and put X's on these springs and these frictions as well, but I don't really need them because the spring is only in the horizontal direction. So you can put it if you want it, but you don't really need it. So I'm going to skip them, but if you want them there, go ahead. And that is MAX. Again, we were only looking at doing the sum of the forces here. So whatever's on the right-hand side of that equation, we're just bringing it down. We're not doing anything with it yet. Deal with it later. One thing at a time. Y'all going to get real tired of hearing me say this by the end of this video. Now we can go and put formulas in for some of these forces. The easiest one is the one we've kind of already talked about, the force of the spring. So let's go and put that in. So now that one's in. We also know that friction is the roughness of the surface, and how hard they are pressed together. Again, we did this the first week. So that translating that sentence into mathematics, we have a force of friction from the floor on the box. Well, that depends on the roughness of the two surfaces and how hard the floor is pressed against the box. Well, a press of one object on another is a normal force. That's what a normal force is it's one object pressed on another. So we can now go on and put that in. Now let's pick the next thing to deal with. Well, the next thing we might want to deal with is this X situation. See, every symbol has to be dealt with. So think about each and every one. What are they there for? What are they telling you? The X is telling us that we only want to look at this horizontal part of the tension. And if we look at this triangle, our tension goes along the hypotenuse here. We only want the horizontal part. We can see that it's going to be the cosine. If I draw it a little bit bigger, maybe make it a little easier to see. There's my force of tension. There's my force of tension rope on box in the X. There's a 90-degree angle. That's a 30. We can do the trigonometry and see that cosine 30 degrees is the force of tension rope on box in the X over the force of tension rope on box, meaning that force of tension rope on box in the X is the force of tension rope on box cosine 30 degrees. And this we know, this is a number. It's 10 newtons given in the problem. We can leave it for now and deal with it later. So let's put that in. Okay, X plus FT RB cos 30 MAX. And now let's take sort of inventory. This we know, it's 10 newtons, like we said. This is a number. This we know, it's 5 kilos. That we know, it's minus 2 meters per second squared because we're slowing down. V is opposite of A, and since V is positive, it's moving to the right, that implies that A is negative. This we know it's 0.2. X is what we're looking for. K we know That was also given in the problem. The stiffness, 20 newtons per meter. But we don't know this. We have one equation with two unknowns. You can't solve that. So we're stuck. And this is sort of the big takeaway and where we left off in class. If you're stuck, do something else. I know it seems obvious, but you'd be amazed how many people don't think to do this. Go do something else. Try another direction, try another force, try another principle, something like this. So another direction or another principle are your two biggest things to try. In this case, we have another direction we can look at, y. So let's go all the way back up and look at y and repeat basically the whole process again. Continuing with our doing one thing at a time. Let's deal with the sum of the forces in y. Once again, a free body diagram can help us with this, but oh wait, we've already done it. So we can just read off. We have a normal force from the floor on the block pointing up. We have a weight force from the earth on the block pointing down. And then our tension from our rope on our block has a y part which points up, and that is going to be MAY. Continuing, doing one thing at a time, maybe start putting some formulas in. For weight, we know that weight is the mass of the object interacting with the planet's gravitational field. So the formula will be mg when we translate that into mathematics. So that leaves us with force normal, floor on box, minus mg plus ft r rope on block in the y is MAY. The next thing to maybe deal with is this little y subscript here. What is the y component of the force? Well, we can use our same triangle as before. And that's going to show us that this one is opposite, so it's going to be sine 30 degrees is the force of tension rope on block y over the force of tension from the rope on the block, meaning that the force of tension from the rope on the block in y is going to be the force of tension rope on block sine 30 degrees, which we can then substitute that in. Force normal floor on block minus mg minus ft r b sine 30 MAY. Continuing on, thinking of stuff to do. We've got MAY. Let's see if we can't figure out what we can do with that. MAY, well, my block, my object, is not moving up and down. So V is 0 and unchanging, which means AY is 0. A lot of people will say AY is 9.8 or something. No, 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 no. Think about the motion. Acceleration is the change in motion, and this block is not moving up and down. So its acceleration in Y has to be 0. So that simplifies our lives quite a bit. Just going to slide down to give myself some more room. Force normal minus mg minus ft awesome. This is a good thing because one of the variables we needed back on X was the force of normal from the floor of the block, how hard the floor and the block were pushed together. That's what's relevant for friction, right? How hard they are pressed together. Now, from looking at Y, we actually know that information. So if we rearrange this and solve for the normal force, we can take that result and substitute it into our X result. So we take this and drop it in there, which gives us minus mu, start a parenthesis, mg plus ft rope on block sine 30 minus kx plus ft rope on block cosine 30 max. And now we're done. We just got to do a little bit of algebra to isolate the one thing we don't know, X, which is also the thing we're looking for. So from here, it's just an algebra problem. So let's do that algebra. First, I'm going to distribute the mu mg minus mu ft rope on block sine 30 degrees minus kx t rope on block cosine 30. And now I'll start shuttling terms around. I'm going to actually take the kx and move it to the other side, like so, leaving me with minus mu mg mu ft and then I'm going to take the ax and move it back across. So that'll leave me minus mu mg minus mu, the tension force from the rope on the block. Remember, mu is the roughness of the two surfaces, how rough they are against as they slide across each other. Now we can go and put some numbers in for all this from our problem. So putting some numbers in, we know mu, the roughness of the surfaces is 0.2. M is 5 kilos. G, the gravitational field of the Earth, is 9.8 newtons per kilo. Mu, again, is 0.2. The tension in the rope was given at 10 newtons. Sine of 30 is a number. Going to a second line because I'm running out of room. The tension in the rope is 10 newtons again. Cosine 30 degrees minus the 5 kilograms for the block. Our acceleration is, as we said, 2 meters per second squared. We already figured that out up here when we thought about the velocity and the acceleration and how they relate to each other. So that we know. And that gives us kx, which when I put all that into my calculator, I get kx is 9.860 newtons. I know what K, the stiffness of my spring, is. So X is that number over K. And I get 0.493 meters, or equivalently 49.3 centimeters. So this string has been stretched 49.3 centimeters, or something in the neighborhood of 16 inches. So that's it. Yeah, it's long. Yeah, there's a lot going on. But if you take our fundamental idea of starting with a principle and doing just one thing at a time, using the math and saying, okay, what in this expression do I not know? Let me figure out what I don't know, unpack it, and just deal with that. You can do it. And like I said, this is what we're going to be practicing basically all next week. This concludes this video.